Hi, just a quick video. One of the things that you can do very usefully with virtual radiography is to replicate experiments that are in the literature. So this is really useful in terms of teaching the science part of the curriculum, but also it gives us the opportunity to deconstruct research and to look about evidence-based practice and try and engage our students in cutting edge research. So to that end, what I've done is I've actually found a paper here which was published only recently by Peacock, Stewart and Riley, and it's a nice little experiment that we can replicate in virtual radiography. So let's have a look at deconstructing it. So in this video, what I'm going to just do is read the paper, not critique it, but read it and find out what the experiment entails, and generate our own data capture form that I'm going to put in a spreadsheet here. I'm ready to do the experiment in virtual radiography. Okay, so we need to, in reading the paper, what we need to know is what the independent variables are. Because any experiment has an independent variable, at least one, which is altered by the researchers, by the experimenters, and so we're going to need something to alter. Now, in this case, just by reading the title, it talks about tube potential, the effect of tube potential. So that's the effect of tube potential. That means that the tube potential was something that was changed. And so that's the independent variable. That's one of the independent variables. So we're going to put tube potential as some people, the other name for this is voltage, tube voltage. I think tube voltage is more common. So that's the independent variable. Okay, and then every experiment has a dependent variable, and often more than one. So in this case, in the title it says the effect of tube potential on clinical image quality. Okay, so the image quality. Okay, now you can measure image quality in different ways, and because this paper is using the term clinical image quality, it's probably not going to be using a mathematical methodology of measuring image quality, which is good for us because when you're doing this with students, you don't want a long delay. You want to be able to get the findings, get the results out quickly. So we want something that's quite quick and easy for the students to measure. So there are measures of image quality like contrast, detail detectability, and modulation transfer function, signal to noise ratio. All these things very complicated and difficult, and you may well lose the students. If you're just using this as an educational tool, then you want something quick and relatively easy to manage and measure. Okay, so we've got an independent variable, which is tube voltage, and we've got a dependent variable, image quality. Now, I don't know, in the title that's all it says. But when you actually have a quick look at the abstract, we get a little bit more. So it talks about dose reduction, radiation dose reduction, and how high KVP techniques are well-known dose reduction methods. And then if we do scroll down a little bit, it says that they're looking at pelvis and lumbar spine radiographs, and they looking at reduction for AP pelvis, reduction dose area product with high KVP is seen. And so they look at dose area product as another dependent variable for radiation dose. So dependent variables, yeah. In fact, we'll put it over here because we're going to be creating a table to put our own data in. So dependent variable 2. So dependent variable 1 is image quality, and dependent variable 2 is dose area product. Now we can use dose area product in because we get that in virtual radiography, so we've got that as well. Okay, so so now that we can create a table now. So if I put that down there, and we'll put some units in. So I like to use units. So the units for voltage are going to be kV. The dependent image quality units is, I think they call it later on, they call it a visual grading analysis. So we're going to call that visual grading analysis. And I think it's, if we scroll down the paper here, when we look at the tables, it gives us the actual score sheet for visual grading analysis, and it's between 0 and 3. So the grading analysis is going to be a score between 0 and 3, and we've got criteria that we can use to score the images. And the dose area product, what units are they using for dose area product? We just look at the paper and we find that out. I'll look in the abstract, because it should have got the dose area product in the abstract there. Milligray centimetre squared. So milligray, and it's multiplied by, a lot of people get that wrong, centimetre squared, and you can superscript the 2 there to make it 2 times. So you go into the font window here and hit superscript. Okay, so that's the units, milligray centimetre squared for dose area product, visual grading analysis 0 to 3, and kVp. Okay, so this is going to be exposures. We're going to have a number of exposures. Now, again, if we're going to replicate this, let's look at their graphs, their methodology, and their results page, see how many exposures they do. Okay, so they do 80 kV and 90 kV, and they do 75 kV and 85 kV. See whether it gives a wider range than that. Just reading it now. So they have a high and low kV groups. So 75 and 85, 80 and 90. Okay, so they haven't got a wide range of kV there, but we'll use their ranges. So the exposure 1, the lowest is 75 kV, isn't it? So exposure 1 is going to be 75. And then exposure 2 is going to be at 80. Exposure 3, well actually what we'll do is we'll just do the 2 extremes. So you should really always do 3. So we've got 75, we've got 80, 85. Well, let's do them in 5 kV. So we've got 75, 80, 85 and 90. That gives us all of the range that they've used. So we get 4 exposures. So we're now going to get 4 exposures. Now what we need to know, and what I'm going to do is I'm going to create this as a table. So there's my table. Now constants, what we need to know is constants. So there must be some constants that we've got to be aware of, because these are variables, but what do we have to hold constant to make our experiment a valid experiment? Well, first thing is what we're x-raying. So they've x-rayed both lumbar spines and pelvises. So I want to make this simple, so we're going to just do one. So we're going to do pelvis. So we're going to do pelvis. Put that over there. So area, or body part. Now they had for their constants for body part were, they had lots of different variable patients, whereas we're going to have just one phantom. So our constant's going to be more constant than their constant, if you like. They tried to keep their sample similar. They had a sample which would be conducive or generalizable to the public. We're going to have a pelvis phantom. Yeah. Next, they probably had a source image distance. Oh, they'll have had a grid, a scatter rejection grid. Now we're going to use a 12:1 moving grid in a bucky, which will be focused at 140 centimeters. I think that's the one that we've got in the bucky. Now they will probably, in here somewhere, if we read it carefully, it'll probably tell us exactly what they used, because that's what you do if you're writing a scientific paper. You have to make sure that we know what's going on in there. So source image distance. So what source image distance did they? Now I actually find it quite difficult to read a paper like this. So what I tend to do is I tend to put it, maybe it's because I'm old-fashioned, but I like to download the PDF or look at the PDF version. Because the double column methodology, the double column way of looking at it is nicer. Oh, it's not gonna show me. Oh, it just takes a while. And then I can search. So I'm going to Control F and search SID. They don't use that terminology. What about FFD? Do they? Distance. What about distance? Okay. Well, we're going to have to read it then. So, see how easy it is to read in this format? I think it's easier. We're just looking for distance. It doesn't really matter because I can't think of a theoretical reason why the distance would change the finding. It's important. It doesn't really matter what distance, as long as it's fixed. I think I can't see it and I can't search for it, so I'm going to just call it. We're going to use 115 centimeters, I think, because 100 may be too small to get. We might get magnified pelvises, which we can't see the bits on. So we'll use 115, and obviously we could be doing source image distance as an effector of radiation dose, but we're not. Now the other thing I noticed here that they're doing is exposure index. So they're going to keep exposure index fixed. They call it deviation index as well. So basically, as they say here, EI is a measure of the radiation reaching the detector, and divided by 100, it's comparable with microgray entrance dose measurement to the detector in microgray. Now, for virtual radiography, we actually have both microgray and exposure index. So, exposure index, we're going to keep to the standard, which is, I don't know whether they say what theirs is, but I know ours is 300. So we're going to use an exposure index of 300, and we're going to try and fix on that. They use an automatic exposure control, so that's fine. Can we think of anything else that needs to be held constant? The centering point, I guess. And that's going to be between the pelvic, the symphysis, pubis and iliac crests in the midline. Maybe that would do. You can look it up and pick. What you would do if you're doing this as a scientific experiment is you would go away and find out what is an accepted sort of centering point, and you would state what you'd centered, how you'd centered. Obviously, when we do one exposure, then it's gonna stay there for the duration once we've done one. Okay, so I think we've pretty much, have we got everything we want? So there are constants. So that's it. We've deconstructed the paper. Now, in terms of our results, we've got a table that we're going to produce our results in. And we've got a score sheet. So let's just take this as a score sheet. What we need to do is I'm going to just grab that. And we'll pop that here for our scores. It's a bit big, isn't it? So we'll make it smaller. Doesn't need to be quite that big. Okay, so that's how we're going to determine our visual grading analysis. And results, how we're going to present our results. So because they've done lots of different patients, they've done 20 patients, they've got their results in this graphical format, which isn't going to really suit us because we're only going to have one patient. So they've got a graph for VGA score. Have they got a graph for dose? Yeah, and they've got a graph for dose. So we're going to be able to do that in bar graphs because we're not going to have this spread along the bottom axis here. What I'll do is I'll just take a grab of these, even though we're not going to replicate them entirely the same. So we're going to have 4 on our, so that's going to be the results for dose. And again, we'll make that a lot smaller. Oh, I've reversed it there. Don't want to do that. And this is just a reminder for me, mental note, these are the things we're going to need to report. And VGA. So just make that smaller as well. So I've now read that paper, taken from it the variables and the constants, and also identified how they measured things and how they reported the results. So that is how you plan for the replication of a paper in your teaching. So in virtual radiography. So what I'll do now is I'll give this paper to the students a week before, ask them to read it and to have an idea about it. And if I've, depends on your learning methodology, I could do this and provide them a worksheet, like this, at the actual time and ask them to conduct the experiment. Or if I wanted them to do a bit more group work, I could get them to generate a worksheet like this themselves in a group and then talk about how they went about that and then conduct the experiment. So during sort of like in a situation where you can't get the students into the campus to do this experiment individually, then this is something that I can do as an experiment in via a screen sharing sort of website, something like Zoom or Microsoft Teams or any of those voice over internet protocol, sort of like video calling softwares. And then they could then be engaged. We could get them to talk to me about it, and so on. So basically, let's just set up for the first exposure, and then we'll. So we're going to do a pelvis 75 kV on the in the bucky, 115 centimeter source image distance. So very quickly, we'll pick up somebody for a pelvis. It doesn't have to be. I'm just going to pick Marjorie Simpson here for who's a walking patient. Make the selection, change this to pelvis. And it's going to be an AP pelvis. And we've got it at 75. So we're going to bring her in, pop her on the table, raise the table up. It's an experiment, so we don't have to do the whole how you would normally consent patients and things like that. We're treating this patient as a phantom on this occasion. So I'm gonna continue to put a marker on though, because it's just habit. Okay, so just checking, I think the marker needs to go down here. Yeah, that's right. If I'm nervous about putting it down there in the pelvis, I'll put it up here in the corner. I can't stop myself, okay, from trying to do good radiography. So I'm going to raise this up to 115 source image distance. I'm reading that off at the bottom there. So I'm reading that off here at 115. I'll bring that across, which is, and just collimate to the size of the receptor. Okay, and now I'm going to keep that the same for all my exposures. So if you were doing this as an experiment, then you'd allow yourself a setup exposure. Obviously they did clinical, so they would be looking at images that the radiographers had deemed acceptable. But we've got the advantage of being able to do a setup exposure, get it exactly right, and then it will be the same for every exposure. So I'll leave that like that. We're going to go to the exposures, and I'll expose this and see what we get with our exposure index. Okay, so that's okay, that's fine. It's probably centered a little low. So I said I was going to center between the iliac crest and the symphysis pubis, which is about there. We're a little bit low, but I'm going to leave that. So our exposure index is 430. So we need to go down by about 50% to get to 300. So I'm going to go down to something like 12. 11 will do. And expose that again. Sorry about the very loud noises. It seems to be set at a very high rate. So 263. Go up one more to 1.5. 298. Bang on, right? Okay, 298 is fine. So that's my first image. So what we're going to do now is take our dose area product reading. So the dose area product reading there is 130 centigrade centimeter squared. So if we go back to our Excel spreadsheet, now they want it in milligray centimeter squared. So centigrade to milligray conversion. Centi is 100th, milli is 1,000th. So it's a times it by 10. So that would be, I think if we want to make it comparable, that's 1,300 milligray centimeter squared. And now visual grading analysis, we could spend some time scoring this. I'm not going to go into the score system, but we'll leave it at that, I think. Well, we'll do all the dose measurements and not do the score measurements. So this is exposure 003. So I'll give it its name, E003. So now what we're going to do is we're going to go up to 80. Can't do 80, we can only do 81. Obviously we're going to have to go down, so the 10 kVp rule would say we halve our MOS if we go up by 10 kV. So if we drop this by 50%, so drop it by 3 to go down to something like 10, then we might get something similar to... So we've got 346 here, 346, so we need to drop it a little bit more, because that's our constant. We can try and keep our exposure index constant. 311, go to 8. 276. So 276, so 9 is probably better. So we'll go to 9. We've already done a 9, which is this one, 311, that's our best. So that's E005. So we go to our Tech Data tab, and the DAP now is 95.1. So go back to our table. So this E005, KV was 81, and the exposure index, I haven't actually put it in as a constant, so we need to put that in as a constant. Sorry, yeah. Insert exposure index. So it was 298 to start with, and this one is 311. So it's as close to a constant as we can make it. 81 kV, and the DAP was 951. Yep. And then we go back to 85. Now should go down to about 6, I think. 6.3, because that's half what was originally 12.5. 269, so go up 1. 303. Okay, and the DAP for that is 91.6. So Alt tab, that's exposure 8. Let's go back to our table again. E008, exposure index of 303, 85 kV, and what was our DAP? Our DAP was 916. It's going to round up, isn't it? 9167, so 917. And then finally, our fourth exposure, 90 kV. So we need to drop this by about 50%, so we'll drop it by about 2. 370, drop it a little bit more. 331, try one more. 298, perfect. So it's 90 and 4.5, and the DAP is 63. So we've got a DAP of 630, and we've got an exposure index of 298, and this is exposure number 11. I'm going to also include insert that's the unit tube charge, because the tube charge isn't a variable. We do vary it, but it's only being varied to allow the exposure index to remain constant. So they used an automatic exposure device in their study, so they didn't record MAS, but we're using a manual MAS to do this. So E11, the exposure index, the tube charge was 4.5. E8, the exposure was 7.1. Uh, 7.1. Sorry, this is 4.5. That was 7.1. This was 12.5, I think. And what was the one in the middle? E05. So go down here. E05 was... That's off the scale. I forgot to record it. I have to go back in the video and work out what those were. But you get the point. You get the point. So now I've recreated that experiment, and now we can draw that graph. So we can actually do a graph which will be analogous to these graphs here, and show the drop-off of dose area product with tube voltage. And as long as the visual grading analysis comes out as equal quality, then what we've demonstrated here is that by increasing our tube voltage, we're reducing our dose area product. So that's a really nice learning moment for our students. So you can see how you can use virtual radiography to deconstruct a research paper, recent research paper. Nice paper there by Peacock et al., published this year. We've been able to recreate that paper to some extent using virtual radiography for a learning moment for our students.